Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show CFD flow simulation of a fluidized bed using SolidWorks flow simulation. In this analysis we have taken a big container with 15 meter height and diameter 5 meter. From side walls we will be injecting coal dust particles at a specific speed, and from the bottom part we will be pushing out steam at a specific pressure and velocity, and at the top we are having some cyclone separators, and these will be utilized to separate out the particulates from this fluid. Initially we will perform one simulation with air and steam, and later on as a post processing, instead of air we will be forcing out carbon dust particles from side walls. Okay, so without wasting time, let us start our simulation. And the leads have already been provided at side walls, wherefrom we will be injecting initially air at a specific velocity, and from down, let us see the down parts. The down part we will be injecting steam, and instead of injecting steam from the bottom side we will be injecting water at 100 degrees centigrade, and next to that we have provided one coil, and that will be generating heat at a high rate. So inside this container, from water at 100 degrees centigrade it will be converted to steam. So phase change of water to steam will be generated inside this container itself, right? So in this analysis we will be forcing out steam from bottom side at a specific velocity, and from side walls we will be injecting carbon particles, and from the cyclone separators the dust particles will be moving out, and the particles with higher diameter will be retained inside this one. Okay, so we're starting this simulation. Leads have already been provided, and the model is made transparent for viewing the dynamics of flow particles. For starting this simulation we have to start the flow simulation environment, and that will be started with wizard itself. Default name of the project we are keeping as project 1. Next, it will be SI system, and pressure we want in megapascal. Temperature will be degree centigrade, and at the same time we want to see that total heat will be in kilowatt. Next, it will be an internal analysis, and definitely heat conduction in solids will be there. Together with that, it is a transient analysis, so we are considering time for this analysis to be 10 seconds, and output time step is 0.1 seconds. That means after each 0.1 second we'll take the results. Gravity is involved, and the direction of gravity is y, so along y it will be minus 9.81 meter per second square, and along z it will be 0. It is a free surface technique, as we are mixing heterogeneous mixture in a single domain. Next, gases. Default gas will be air, and initially water will be there for the liquid. Instead of steam we are considering water at 100 degrees centigrade, and at the bottom of this container we have provided one heater that will be generating huge amount of heat. So because of that, this water at 100 degrees centigrade will be converted to steam. That means we want to have a change of phase inside this container only. We have taken air and gas as immiscible fluids. Next, the container will be made up of alloy steels. Let us consider the material as stainless steel 321. Next, default outer wall thermal conditions and roughness we are considering. Next, let us consider the temperature to be 20 degrees centigrade, and pressure should be 0.1 megapascal. Initial concentration it will be 100% air. That means the container will be filled up with air. Again, during application of boundary conditions we will be injecting air, and by the same time we will be injecting water from outside. Again, solid parameters, it will be having temperature 20 degrees centigrade. Let us finish this. This is the computational domain. We can hide this, and we can apply our boundary conditions. Initially you have to apply the heater that will be generating steam from water at 100 degrees centigrade. So we can provide heating surface from conditions and surface source. Let us provide heat at 10 kilowatt. Let us select the heating surface as this bottom one. It is made in the form of spiral. We can rotate this object to understand the geometry in a better way. Let us rotate this. You can see this spiral. That spiral coil will be generating heat at a rate of 10 kilojoules per second. That means 10 kilowatt heat is provided at the base, and that will be converting water at 100 degrees centigrade to steam. Grain check. This is done. Let us see the front view. And for applying boundary conditions, it is always suggested to have a segmented view of this model. So for providing boundary conditions in a better, we will cut this model from top plane. Let us cut this one from top plane and drag it down to select that locations for applying boundary conditions. Now we can rotate this one a little bit. Yes, right, this is okay. Next to that, we have to apply boundary conditions. It is having only one fluid subdomain. Inside this fluid subdomain, we are mixing water and air as two different heterogeneous mixes using free surface techniques. Boundary conditions, insert boundary conditions. Initially, we want to provide air from the side walls at a specific velocity. Let us provide air at a velocity of 60 meters per second from the side walls, and thermodynamic parameters, it will be normal temperature and pressure, and substance concentration, it will be only air. We can select that location of air. We can rotate a little bit to select the other locations. So from these side walls, we will provide air at a rate of 60 meters per second. Grain check. One boundary condition is applied. Next one, we have to provide water from the bottom side at a rate of 60 meters per second. So boundary conditions, insert boundary condition, and we want to provide water at 100 degrees centigrade with a velocity of 60 meters per second from down position. Velocity will be 60 meters per second like before, and thermodynamic parameters, it will be having temperature of 100 degrees centigrade, and substance concentration, it will be 100% water. The location we are selected. So from down portion, we are providing water at a temperature of 100 degrees centigrade with a velocity of 60 meters per second. After passing from this location, it has to pass through this heater, which will be generating heat at a rate of 10 kilowatt. So grain check. Another boundary condition is required, that means atmospheric pressure at the exit location. So we can see the model in a different way. We have cut this one along front end. Now we have to apply boundary conditions from top side. So boundary conditions, insert boundary condition. It will be atmospheric pressure or environmental pressure at the exit location. We can rotate a little bit to select that location in a better way. Rotate view. Selected. Green check. All the boundary conditions have been applied properly. Next one, we can select some goals. Our plan is to have some global goals, that means average temperature of fluid, average velocity, at the same time volume fraction of air and volume fraction of water also. We are selecting some global goals. Insert global goals. We want to have average temperature of fluid, average pressure, and average velocity also. But at the same time, we want to have goals like average volume fraction of air and average volume fraction of water. These are the different global goals selected. All the goals have been defined properly. Next, we want to have better mesh to have the results in a better way. So we're going for global mesh, and we can edit these things manually. Let us edit this mesh manually, and we want to go for some kind of refinement. Let us see the refinement level. It is refined up to 1 level, so we can see that meshing is not perfect. We can refine up to 3 level. And advanced refinement, small solid features refinement, it is not required. Even here, curvature level, that is also not needed. Tolerance level is not that much of important. So we are refining the mesh up to level 3. Green check. Before initiation of this flow simulation, we have to see the calculation control options. And from here, we'll see the saving option, and from here, periodic, and we have to select some parameters like immiscible air, immiscible water, and volume fraction of air. By the same time, we want to have volume fraction of water. Done. Next to that, we can run with new calculations. Solver has already started iterations. Mesh preparation is going on. Let us see the results from the solver window itself. All the goals we have selected. Together with these goal plots in graphical representation, we want to see these things in a different way also. Let us view these things in a different way. We want to see these graphical plots together with the actual representation of this simulation. Let us see the temperature of fluid and image attributes. Let us make this little bit smaller. These are the actual images. Together with that, we want to see our results in the form of graphs. As it is a transient analysis, at different times we'll be getting different results. And this is temperature distribution, and you can see how temperature is moving from bottom to upwards. It is showing that maximum temperature is 100 degrees centigrade and minimum is 20 degrees centigrade. From the graph also you can see average temperature of fluid is 69 degrees centigrade. As the number of iterations is 75 only, at this moment temperature is also changing inside. And average velocity is 17.37 meter per second. And volume fraction of air, it is 78%, and that of water is 21% at this moment. Initially the container was filled up with air, and from the bottom side we are forcing out water at a specific velocity. So we can see solver is finished right now, and from the solver we can see the results that average temperature of fluid is 68.189 degrees centigrade. Average total pressure is 56 megapascal, that is very high, and average velocity is 17.4 meter per second. Average volume fraction of air is 78%, and that of water is approximately 22%, right? So these are the results we have seen from solver window. Next to that, we want to see these things in the form of cut plots and other things. So from this one, as a post-processing, we'll see the particle study using carbon particles. Initially, we'll see the goal plots. So with the transient explorer on, starting the transient explorer, this is on. Now first of all we'll see from cut plots, insert cut plot. We want to see from front plane. and we're going to see the velocity in the form of contours and vectors also. Let us see. Let us stop this one and we can see something else. Let us see temperature of fluid. Temperature of fluid we want to see. You can see how the temperature of fluid is changing from down to up, and by the same time we are injecting air from side walls. Blue color indicating temperature of air from side walls is 20 degrees centigrade, and water which is being forced out from bottom side, which is having temperature of 100 degrees centigrade, right? Let us see these things in the form of animation. Next to that, we want to see something else like immiscible mixture of air and water. We can see cut plots, insert, and we want to see something else like immiscible air. We want to see grain check. Next one, we'll see immiscible water from cut plots. Edit definition, and we want to see immiscible water. Let us close these things. Let us see pressure also. First one, let us clear and hide. We'll see pressure distribution also. This is pressure distribution. Next to that, we want to see surface plots. Let us clear and hide these things, and we want to see surface plots. Insert. Use all faces, and we want to see temperature of fluid at the surfaces. This is a surface plot which is indicating temperature of fluid at different locations. Different temperatures are there. At the bottom side we are having higher temperature, which is 100 degrees centigrade, and as it is going up, its temperature is varying. You can see here average temperature is in the range of 60 to 68 degrees centigrade, which is indicated by green color. Next to that, we want to go for post-processing. That means carbon injection will be there from side walls, and we want to go for particle study using carbon dust particles. Let us close these things. Surface plot 1, we want to close it. Let us clear and hide these things. Transient explorer to be off also. Next one, we want to go for particle study. That means we want to inject carbon particles from side walls, and from down, as usual, steam will be passing out. Okay. Instead of steam, what we are doing, we will be injecting water from down at 100 degrees centigrade, and while passing water at 100 degrees centigrade, it has to pass through one heater which will be generating heat at 10 kilowatt. So definitely there will be some change of phase from water to steam inside this container. Particle studies, starting with wizard, you can go for the next one and giving the name of the study as particle study 1. Total numbers of particles in this case 20, we can make it 200 for seeing these dynamics of flow particles in a better way. We're making these particles numbers to be 200 numbers, and particles diameters we're making it to 0.30, 5 meter. And instead of liquid we have to inject carbon particles, so we can select solids from here. In normal material list we don't have carbon particles, so we have created a new material in this case, and that will be carbon particles. We have made this one providing the properties of carbon materials. This is user defined material. A mass flow rate to be 1 kg per second. Initial velocity is not required, and temperature of that one will be definitely 20 degrees centigrade. That will be passing from the side walls. We have to select that locations. You can rotate this little bit for selecting the locations in a better way. This is done. Next we want to inject water from bottom side at a temperature of 100 degrees centigrade. So more injections are needed. User defined liquids, it will be water at 100 degrees centigrade. Mass flow rate of water will be 1 kg per second, and temperature will be absolute 100 degrees centigrade. We have to select that location for water. Selected. Next, erosion will be there. Accretion is not required because accretion is actually involved when there is an accumulation of particles. So we are considering erosion and gravity, and the direction of the gravity is y. Next, we are considering ideal reflection inside the walls. That means after reflecting at the boundary walls, it will be bounced back properly. Next one, we want to see trajectories and statistics. Next, let us run these things. So you can see 2 injections are there. That means injection of carbon dust particles from the side walls and injection of steam or water at 100 degrees centigrade from downwards. Let us run these injections 1 and 2. Let's play all. We want to see the complete view of the model, and let us see these things from front end. Let us see the animation of these things. From down we are injecting water at 100 degrees centigrade, and while this water is passing through these heaters, it suffers a change of phase from water to steam. And from side walls we are injecting carbon dust particles at a rate of 1 kg per second. Now we can see how this mixing of water and carbon dust particles are taking place inside this container, and this is the temperature distribution of fluid inside this container. From this color distribution of particles, we can see that average temperature is in the range of 67 to 75 degrees centigrade approximately. Next to that, we want to see something else like surface parameters. Let us see surface parameters. Insert surface parameters, and you see all the parameters like density of fluid, solid. Let us select all these things. Let us see the surface parameters inside the walls. So select other, selected. Now I want to see the surface parameters. Let us show all these things in the form of surface parameters. At the side walls, we want to see all the results. You can see pressure at the side walls is very less because at the boundary pressure will be less. It is 0.1 megapascal. Density velocity at the boundary, it is 0 definitely. And you can see some other things like turbulent time, etc. You see mass fraction of water, air, etc. at boundary. So following this technique, we can see surface parameters at different surfaces, right? Together with that, we have some integral parameters like heat transfer rate, number of particles 430. These are the results obtained from surface parameters, right? Let us close these things. In this particular study, the velocity of carbon dust particles was 60 meter per second and that of water was also 60 meter per second. Now, instead of stopping it here, we can go for similar type of particle studies with different velocities of carbon dust particles and water. And we can have a parametric study of all these results with different injection velocities. And from this parametric study, we can have a better understanding of mixing of water and carbon particles. And you can see how many particles are going out, how many particles are being accumulated at the bottom side, etc. can be viewed. Okay. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.